Howdy! Here we go, chapter 3, lesson number 11, integration, but using inverse trig functions. So what is this all about? Well, if you think back to the differentiation chapter, we were differentiating our inverse trig functions. So we were differentiating sine to the minus 1 of x, and we found that we got 1 over the square root of 1 minus x squared, and when we differentiated tan to the minus 1 of x, we got 1 over 1 plus x squared. If you reverse that, flip it, then it means if you integrate 1 over the square root of 1 minus x squared, you will end up with, you got it, sine to the minus 1 of x. And if you integrate 1 over 1 plus x squared, you will get tan to the minus 1 of x. Perfect. What you can do is you can show that that can be extended to give, well, if you have instead 1 over the square root of a squared minus x squared, that gives sine to the minus 1 of x over a plus c. And if you have 1 over a squared plus x squared, if you integrate that, then that gives you 1 over a tan to the minus 1 of x over a plus c. This here is on your formula sheet. You are given that. You don't need to remember it. You just need to know how to use it. So let's go into some examples. Example 1, integrate 1 over the square root of 9 minus x squared. So you can see it is in this form here. But what you need to do is you need to think, right, well, I've got 1 over the square root of, and I've got a squared minus x squared. Here, I've just got 9 minus x squared. So you need to write the 9 as something squared. That way you can have the square root of something squared minus x squared. And we all know 9 would be what squared? 3! Perfect! So that is 1 over the square root of 3 squared minus x squared. So that is what you're integrating. And if you have that, well, you can see that sine to the minus 1 of x over a. So because we've got 3 squared here, that will be sine to the minus 1 of x over 3. Perfect. And in the end, plus c. You got it. Well done. Example 2, integrating 1 over 16 plus x squared. So this one here, have a look. Well, you can see that is in this form here. But what do you notice? Well, we've got 1 over. We've got an x squared, They've got a squared, and here we've got a 16. So once again, you need to do the same thing. We need to write 16 as something squared. And we know what the 16 would be. Perfect, it's going to be 4 squared. So we can rewrite that as 1 over 4 squared plus 16 squared. So that is what we will integrate. And if you do that, well, you can see that because we've got a squared, that goes to 1 over a at the start. So we will have at the start, because it's 4 squared, 1 over 4. Then we'd have tan to the minus 1 of, and x over a, in this example that we are doing, would become x over 4. Plus c. Example 3, integrate 1 over the square root of 5 minus x squared. Once again, you're thinking, ooh, I recognize that. That looks an awful lot like this at the top. It's the square root of a squared minus x squared. But what you'll notice is that everything's fine for this, except there is an a squared there, but we have 5. And 5 is not a square number. But that doesn't stop us, because we could still write 5 as something squared. What squared will give us 5? Perfect, just the square root of 5. So that becomes 1 over the square root of, and 5 becomes the square root of 5 squared. Take away x squared. So don't worry, we can still do it. From there then, that will be sine to the minus 1 of, so sine to the minus 1 of, and x over a would become x over the square root of 5 plus c. Example 4, integrate 4 over x squared plus 36. So with this one again, you're thinking, ooh, I recognize that form. It looks an awful lot like this. So you're right, it does, except there is a 1 at the top here, and we have a 4 at the top. However, don't let that put you off. Look down at the bottom row, there's an x squared plus 36. Well, I really need it in the form of something squared plus x squared. But I know that that's just flipped around, and really 36 is the same as 6 squared. So I could write that just as easily as 4, because I'm not doing anything with that, over, and then x squared add 36 is the same as 36 add x squared, which will become 6 squared add x squared. From there, again, this 4, what would you do with the 4? Help me out. Nothing. Exactly. You just leave the 4 as it is. So we leave that as 4. Imagine that as 4 times 1 over. And then 1 over 6 squared plus x squared would become 1 over a. So in this case, it's 1 over 6. Tan to the minus 1. And then x over a would become, in this case, x over 6. And again, on the end, you'd have your plus c. Simplify that, 4 times 1/6 would be 4/6, and that simplifies to 2/3. So we'd have 2/3 tan to the minus 1 of x over 6. Example 5. Integrate 1 over 20 square root of 25 minus 9x squared. Uh-oh, problem. Look, we don't have a something squared minus an x squared. We've got something squared minus 9x squared. Well, ignore that for now. The 25 we can easily, based on the other examples, we know we can just write that as 5 squared. That's absolutely fine. But what we need is x squared. We need an x term squared. So what we need to think is, what would the x term be that when you square it, you would get 9x squared? Perfectly right. It would be 3x. If you square 3x, it will give you this 9x squared. So from there, if we're integrating, well, what we're thinking is, well, we know that when it's the square root of a squared minus x squared, it's sine to the minus 1 of x over a. So here we'll have sine to the minus 1 of, and instead of x, well, we've got 3x. We're not just squaring x, we're squaring the 3x. So it'll become 3x over, and a in this case, what are we squaring? What number are we squaring? We're squaring 5, so it'll be 3x over 5. However, you don't just leave it there. What you need to do is you need to think, right, well, in the brackets here, I've got a 3x. And when you're integrating and brackets are involved, what you need to do is you divide by the derivative of the brackets. Here, if you differentiate the 1, the x, you would just get 1, so we would divide by 1, so that's not changing. However, we're taking away 3x squared. So you differentiate what you're subtracting, the 3x, and if you differentiate 3x, you get 3, so we're also having to divide by the derivative of the brackets. So as it says here, x has been replaced by 3x. So we have to remember to divide by the derivative, hence that third. That is why that comes into play. Example 6, integrate 1 over 9 plus 4x squared with respect to x. So first thing again, you're thinking, ooh, I recognize that form. It looks an awful lot like this, and you're right, it does. We've got something squared. We've got the 9, but we can write that as 3 squared. We know that. But instead of an x squared, we've got 4x squared. So we're thinking, what would the x term be that you square to get 4x squared? Well, that would become 1 over 9 is just 3 squared plus, what would it be? 2x. Good. If you square 2x, that will give you the 4x squared. Perfect. So for this one here, we have 1 over a. A in this case is going to be 3. So we've got 1 over 3. We then have tan to the minus 1. And then x over a. Well, in this case, it's not just x squared. It's 2x squared. So it'll be 2x over. Good. 2x over 3. Perfect. And then plus c. However, once again, x has been replaced by 2x. And when you have that, you need to divide by the derivative of the brackets. Differentiate 2x, you get 2. So we're also dividing by 2, or multiplying by 1/2. So, as it says here, x has been replaced by 2x. So we have to divide by the derivative. Differentiate that, you get 2, so we're dividing by 2. From there, simplify that. 1/2 times 1/3 would be 1/6. Tan to the minus 1 stays. 2x over 3, and the plus c would all stay as they are. And that's your answer. R. Example 7, integrate with respect to x1 over the square root of 9 minus x squared between 3 and 3 over 2. So with this one, what we're thinking is, ooh, I recognise that. It looks an awful lot like this at the top. We've got the square root of something squared minus x squared. But 9, you need to rewrite first of all as, you got it, 3 squared. Good, so you're integrating 1 over the square root of 3 squared minus x squared in order to get it in this form. Once you do that then, well, if you integrate that, you know you're going to get sine to the minus 1 of x. And then x over a, well, what are you squaring? Well, we're squaring x, so it'll be x over, and what's the number? 3, so it'll be x over 3. And we're integrating that between the limits 3 and 3 over 2. From there then, if you sub in these values, you'll have sine to the minus 1 of x. If it was 3, you'd have 3 over 3, which will give you sine to the minus 1 of 1. Take away sine to the minus 1 of, if you have 3 over 2 divided by 3, well, 3 over 2 is really 1.5. Divide that by 3 and you're left with a half. Or the times by 3 on the top and the divide by 3 will cancel, leaving you with sine to the minus 1 of a half, no matter which way you do it. From there, inverse sine of 1 will give you pi over 2. If you just think about the graphs, think about the sine graph is going to have a maximum there of 1 at 90 degrees. Sine to the minus 1 of a half is going to be 30 degrees. Use the exact value triangles or the table if you've memorized it. 30 degrees, remember, keep it in radians, pi over 6. After that, to subtract the fractions, you need the same denominator. So, write pi over 2 in terms of sixths. How many sixths is that? Good, that's 3 sixths. So you'd have 3 pi over 6 minus pi over 6. From there, 3 pi, take away pi is 2 pi, num num num, over 6. And then from there, if you divide the top and the bottom by 2, you're left with pi over 3. So that will be your answer. Woo! Example 8, integrate 1 over 4 plus x squared between 2 and negative 2. Once again, you're thinking, ooh, I've got it in this form. I've got something plus an x squared in the bottom. It looks an awful lot like this. And you're perfectly right. So, you are going to integrate between 2 and negative 2. But if you write it in the form of 1 over a number squared plus x squared, what number will you square, Piotr? Good, 2, so that would be 1 over 2 squared plus x squared. And then after that, you can integrate. When it's in this form, look at the formula sheet. It'll be 1 over whatever number you are squaring. So it'll be 1 over 2, and then it's tan to the minus 1, and then you've got x over a. Here, the x term that we are squaring is x, so it'll be x over, and the number we're squaring is 2, so it'll be x over 2. Make sure you don't have plus c because you've got the limits, 2 and negative 2. After that, you will sub these in, so 1/2 will stay as 1/2. Tan to the minus 1 of, if you sub in 2, you'll have 2 over 2. You could write that, but you know 2 over 2 is just 1. We are taking away half tan to the minus 1 of, and if you sub in negative 2, negative 2 divided by 2 is negative 1. After that, you will have 1/2 tan to the minus 1 of 1 is going to be 45 degrees, or in other words, pi over 4. Tan to the minus 1 of negative 1, you can either think about the graph, and that will just be the negative of tan to the minus 1 of 1, which will be negative pi over 4. And then from there, you're multiplying each of these by a half. So a half times pi over 4 will give you pi over 8. And then you're taking away the negative, which will mean add. 1 times pi is pi, 2 times 4 is 8. So we've got pi over 8 and pi over 8, which will give us 2 pi, num num num, over 8. And divide the top and the bottom by 2 will give you pi over 4. Woo! Keep your answer as that. Remember, you use radians in advanced higher. Example 9, use the substitution. Ooh, it's more integration by substitution. U equals x take away 3 to find the integral of 1 over x squared take away 6x plus 13. So, first thing we are thinking is, our substitute is u equals x take away 3. So, what we want to do is we are wanting to write all of this in terms of u. So we've got this substitute, so we know u has to go in here. We want to do two things then. We are wanting to have x in terms of u, and we're also wanting to have dx in terms of u. Doesn't matter which one you do first. If you get dx in terms of u, you get that by differentiating u. So if we differentiate u, we will have du by dx, and that will give us just 1, because if we differentiate x, we're left with 1. From there, multiply both sides by dx means then that du will equal dx. Woo! So we have dx in terms of u. We know that will equal du. We then need to write this bit at the bottom in terms of u. How would we go about doing that? Drew, what do you think? Perfect. If you know that u equals x take away 3, then you will know that x is equal to u plus 3. So you add 3 to both sides. So we now know what x is in terms of u. But we've got x squared take away 6x, so we also have to write that in terms of u. So that will become, well, since u equals x take away 3, x will equal u plus 3. And now you replace the x with u add 3, so we'll have u add 3 squared. Take away 6 times u plus 3 plus 13. From there, if you multiply out the brackets, u plus 3 times u plus 3, well, u times u is u squared. U times 3 is 3u plus u times 3 is 3u, which will give you 6u. 3 times 3 is 9. You'd have take away 6u, take away 18, and then plus 13. And if you simplify that, it gives you, good, u squared plus 4. So now then, we can write the whole of this bottom line as u squared plus 4. So that will then become 1 over u squared plus 4. And remember, dx is du. From there, we are thinking, how do we integrate that? Well, think of your inverse trig terms. Because you have 1 over, and then if you've got a squared plus x squared, it will go to this formula here. Because we are integrating with respect to u, well, we've got a u squared and we've got a number. If you write this number out as some number squared, that would be 1 over, and then flip it back to front as well, just so it looks like this. Number squared plus x squared, but instead of x it's u, so number squared plus u squared, you get that. From there then, you'd have 1 over a, so our number that we're squaring is 2, so it will be 1/2. We will have tan to the minus 1 of, and instead of x over a, we'll have u over a. And remember, a was 2, so it'll be u over 2. What do we have in the end? Plus c! You got it. And then from there, the final step would be, if we are integrating, we're using this substitution, so we would then replace u back with what it's equal to, and it's equal to x take away 3, which means we'd have a half tan to the minus 1 of x take away 3 over 2 plus c. And that would be your answer. Example 10. Use the substitution u equals 2 sine x to find the integral of cos x over 1 plus 4 sine squared x. So for that, again, we are given this substitution. We are told that substitute is u equals 2 sine x. We need to then rewrite all of this in terms of u. So to do that, it doesn't really matter what we're doing first. I'm going to start off by differentiating u. So if I differentiate u with respect to x, I would have du by dx would be 2 cos x. And multiply both sides by dx would give me du equals 2 cos x dx. From here, what I want to think is, well, I want to express all of this in terms of u. And to write it in terms of u, what I want to do is I want to try and think how is the best way to do that. So I've got this 1 plus 4 sine squared at the bottom. What you need to recognize is that 2 squared gives you 4. And if you square sine, you will get sine squared. Which means if you square this to sine x, you will get 4 sine squared. So really this becomes 1 plus 2 sine x squared. And if you square that, you'll get the 4 sine squared, which means then you can replace this 2 sine x with u. So that becomes 1 plus u squared. So this bottom line will be 1 plus u squared. But we've also got this cos x dx. So let's go back to that derivative, and we just found out that du equals 2 cos x dx, but we want cos x dx. So to get rid of the 2, we divide both sides by 2, and that'll let us know what cos x dx is equal to. So cos x dx will equal a half du. So from here, we will have, well, if we split this up, so we've got cos x just at the side, we'd have 1 over 1 plus 4 sine squared x. But that will become 1 plus 4 sine squared x was equal to 1 plus u squared. So that will be 1 plus u squared. And then cos x dx was a half du. But the last bit, as I'm sure you've noticed, is you have to express your limits in terms of the new variable. So the limits must be written in terms of u. And to get that, you need to think, right, well, here they're in terms of x. So when x is, let's take the bottom limit, when x is 0, well, you can replace x with 0 here. So u would equal 2 times sine 0, which is just 2 times 0, which is 0. So the bottom limit is 0. And then when x is pi over 6, you replace x with pi over 6. So it's 2 times sine of pi over 6. Pi over 6 is 30 degrees. So it's 2 times, which is going to give you a half. So it'll be 2 times a half, and then that will give you 1. So the limit at the top is 1. So now we're wanting to integrate 1 over 1 plus u squared times a half du between 0 and 1. So to do that, well, a half is just going to stay as 1 half. And then if you think about this formula here, well, you've got 1 over a squared plus x squared. A, in this case, is just going to be 1. So we'd have 1 over 1, which will disappear. We'd have tan to the minus 1 of x over a. But x, remember, is u, so we'll have u over 1, but that is just u. So we're just left with that half, and then that just becomes tan to the minus 1 of u. From there, sub in 1 and 0, so you would have a half times tan to the minus 1 of 1. Take away a half times tan to the minus 1 of 0. Tan to the minus 1 of 1, if you think about your exact value triangles, that just gives you 45 degrees. In terms of radians, that'll be pi over 4. So it's a half times pi over 4. Take away a half times, and tan to the minus 1 of 0, use the graph, that'll just be 0. Which means then you are left with a half times pi over 4, which will give you pi over 8. And that is your final answer. There are 10 examples with inverse trig functions, applying them to integration. Best of luck. Try these questions in the booklet, page 66, page 67. Give them a shot, see how you get in. Just remember to use these formulas, which are on the formula sheet. Best of luck. Bye.